Hello everyone, my name is Hsieh-Yu. Today I would like to share our work with you, a controller design for smooth transition in physical, human, robot, and environment interaction. This transition happens between two modes. One is augmentation, the other one is autonomous. So let's get started. First is our background. Our first background is physical human-robot interaction. So there are many types of collaborative robots, depends on task. The one we focus on is here. We have a robot, human, and we mount a force sensor on the end effector. The force sensor will measure the human force, and then we design a controller scheme to transfer this human force to robot velocity, and then so that the human can compliantly direct the motion of the robot. So here's one of the examples. The human can direct the motion of a robot based on their intention because the whole cooperation is compliant. Secondly, we have the second background, which is physical human robot and environment interaction. The idea is here, the human guide the robot to contact an extra environment. The environment will give the robot an environmental force feedback. This environmental force feedback is defined as any external force on the end effector minus this human force. So the problem is here when three of the objects are in couple, it will cause unstable interaction. And how researchers solve this problem is that they use two force sensors to decouple these two forces. And then they can design a control law to balance these three interactions. So the application is human-robot augmentation. Let's say we try to insert a nail into a wood. The interaction force is quite strong. It's quite hard for us to insert this nail with our hand. But with a robot that augments our force, we can easily do this task with our little finger. This is because the whole cooperation is compliant, and then the interaction is also stable. We call this type of robot is controlled in augmentation mode. Next is our research motivation problem. So there's actually one downside using this controller in this type of interaction. That is, the human has to keep pressing the environment. This is because the controller is a force control. The human let go, so when the human lets go of the robot, there's no desired force. Then the environmental force feedback will push the robot away. One of the examples is a medical robot for kidney stone image scanning. So here's the example. We mount an ultrasound probe on the end effector of the robot to scan a phantom. This phantom has a embedded kidney stone inside. Here's our ultrasound image. As you can see, we need to have a strong interaction force for a clear image. So when humans release the robot, these two items no longer in contact. The image will become blurred. So imagine in the real surgery, the surgeon needs to keep pressing the patient, which is really inconvenient and troublesome. So it seems that the source of gap is that the robots require another type of interaction, which is physical robot environment interaction. The main idea is here that when the human guides the robot to the desired position, when he let go, the robot can change the control scheme and to maintaining this axis, this position, and also keep in contact with the object. The troublesome part for here is that when controller schemes switch from here to here, there's a risk to cause instability. This is because first, in terms of this axis, we change from force control to position control. The whole controller structure change, they will cause the risk of unstable interaction. Secondly, a net force drop in terms of this axis after the human release the robot. Then the controller will try to increase the torque to maintain these forces, and it also causes another risk to create the overshoot in the transition. Lastly is the controller parameter for different interaction are different. So let's say here we actually want a compliant cooperation so that human can easily guide the robot. But after human let go, here we actually want a rigid interaction so that the robot can strongly in contact with the environment. So these three challenges are our research problem. To solve the problems, we propose a control scheme. But before we introduce our controller, we actually want to share two definitions that used in this paper. That is two modes. The first mode is augmentation mode. The augmentation mode is defined that human can direct the motion of the robot based on their intention. And then normally the controller is an admittance control in the outer loop and velocity control in the inner loop. The interaction involved including the traditional physical human-robot interaction and the one with the environment. On the other hand, autonomous mode is defined as a traditional collaborative robot, which is the robot have a predefined position and force command. The controller is impedance control in the outer loop and position control in the inner loop, so that the robot can maintain the position in consideration of the environmental force. The interaction including the interaction with human and without human. So this is the definition of two modes. Then we propose a control scheme to switch between two modes. In the outer loop, we use a very unified admittance and impedance control. The variable terms here is to solve the problem that different situations require different interaction. Say sometimes we need compliant, sometimes we need rigid interaction, depends on the tasks. So the impedance or admittance parameter will change based on the situation. And in the inner loop, we propose a unified position and velocity control to switch between two modes. And adaptive turn here is simply to solve the uncertainty from the robot dynamics, which is a traditional problem in the adaptive control. So the overall approach is here. In the augmentation mode, we have a variable admittance control and adaptive velocity control. When we do the transition to maintain the position axis and maintaining the contacting axis in the autonomous mode, we use the variable impedance control and adaptive position control. And here's our formulation. In the outer loop, we have a proposed variable impedance and maintenance control with our update load. There are three terms. The first one is the admittance and impedance control with mass, damper, and stiffness. And we propose a transition factor to switch from augmentation mode to autonomous mode. Then the target force is in consideration with three forces: human force, desired force, and environmental force. And then we use the update load to update this damper, update this damping. Two of the update load are from the traditional one, human and environmental force, to guarantee when human, robot, and environment are coupled together, the interaction is stable. And then in this paper, we propose the transition turn to guarantee a smooth transition. After we define the outer loop, the inner loop is relatively simple. So we have the unified adaptive position and velocity control by modifying the starting factor that with a consideration of our transition factor, so that the controller will change from position to velocity or velocity to position by itself. And another good thing about this idea is that the controller and the update load can be proposed in a traditional form. Yeah, so this is our formulation. The other two things I want to mention is the implementation and proof. So to save the cost, instead of using two force sensors, we use one force sensor and one force estimator. And then to use this force estimator, one of the issues that we need to consider convergence. So in our proof, we have passivity and stability in the outer loop and inner loop. We also consider the convergence of the triplet and force estimation. So if you are interested in more details, do check our paper. Next, we have our experiments. We conduct 3 experiments. First is a transition in the position maintaining axis. So here's our experimental setup. We have a 3D freedom robot in a Cartesian form, 1, 2, 3. And if we zoom in any factor, we have the human, a force torque sensor that measures the human force, and a switch for the human to switch the controller scheme. So the first experiment is as follows. The human will guide the robot into the desired position, marked as a black tape here, then transfer from the controller scheme from augmentation mode to autonomous mode. In this whole experiment, we don't consider any environment here. But we compare with the traditional method, which is a position control in augmentation mode, and switch to the force control in autonomous mode. So here's our result. As you can see, proposed method and traditional method, human pull the robot to the desired position and then switch. As we can see, the traditional for the traditional controller, we have a very obvious oscillation. The maximum overshoot is around 5.8 mm. However, our proposed controller achieves almost 0 millimeter overshoot. And the second experiment is a transition in the contacting axis. So again, we have a 3D freedom robot. We have another extra environment, a wood platform. Then the human will guide the robot with an extension in the end effector to contact with this environment, press this environment using a sufficient force. The whole experiment, we also compare with the traditional method, which is variable admittance control. We switch from human force in augmentation mode to a constant desired force in autonomous mode. The experimental results as follows. We have a proposed and traditional control, move the robot to in contact with the environment using sufficient force, and switch to the control scheme. And as you can see here, the traditional method have a significant overshoot around 17.2 newtons. Since the ground truth is around 55 to 60, so the overshoot is around 30% compared to our proposed method. The proposed method is only around 10% overshoot, which is 5 newtons. So this is our second experiment. Our last experiment is a transition between 3 interactions. So we change the environment here. We use a wire crimper as an environment because the interaction force is really strong, as we can see here. If the robot in augmentation mode is compliant, when the human releases the robot, the environmental force will push the robot away. With our control scheme, we can see here, there's no oscillation when we switch the controller into the autonomous mode. As you can see, the whole interaction is stable, and when we switch back, still no oscillation. The whole transition is smooth. So this is our last experiment for 3 of the interactions. Lastly is our conclusion. So in this paper, we propose a controller for smooth transition in physical human-robot and environment interaction. The controller can be stably transferred between 2 modes. One is augmentation, the other one is autonomous. So with that, I end our presentation here. Thank you.